when I don't use my hands. Notice how this pole has a reflective marker on top, which means that it can be located in the space. You can notice that this quad is making fine adjustments to keep the pole balanced. How did we design the algorithms to do this? We added the mathematical model of the pole to that of the quad. Once we have a model of the combined quad-pole system, we can use control theory to create algorithms for controlling it. Here you see that it's stable, and even if I give it little nudges, it goes back to the nice balanced position. We can also augment the model to include where we want the quad to be in space. Using this pointer, made out of reflective markers, I can point to where I want the quad to be in space, a fixed distance away from me. The key to these acrobatic maneuvers is algorithms, designed with Notice how the quad lost altitude when I put this glass of water on it. Unlike the balancing pole, I did not include the mathematical model of the glass in the system. In fact, the system doesn't even know that the glass of water is there. Like before, I can use the pointer to tell the quad where I want to be in space. Okay, you should be asking yourself, why doesn't the water fall out of the glass? Two facts. The first is that gravity acts on all objects in the same way. The second is that the propellers are all pointing in the same direction of the glass, pointing up. You put these two things together, the net result is that all side forces on the glass are small and are mainly dominated by aerodynamic effects, which at these speeds are negligible. That's why you don't need to model the glass. It naturally doesn't spill, no matter what the quad does. The lesson If we analyze the mathematical model of this machine with only two working propellers, we discover that there's an unconventional way to fly it. We relinquish control of yaw, but roll, pitch, and acceleration can still be controlled with algorithms that exploit this new configuration. Mathematical models tell us exactly This quad has a racket strapped onto its head with a ball so that it flies to where it was thrown from. Third, a trajectory is planned that carries the quad from its current state to the impact point with the ball. Fourth, we only execute 20 milliseconds worth of that strategy. 20 milliseconds later, the whole process is repeated until the quad strikes the ball. Machines can not only perform dynamic maneuvers on their own, they can do it collectively. These three quads are cooperatively carrying a Skynet. They perform an extremely dynamic and collective maneuver to launch the ball back to me. Notice that at full extension, these quads are vertical. In fact, when fully extended, this is roughly 5 times greater than what a bungee jumper feels at the end of their launch. Interaction doesn't have to be virtual, it can be physical. Take this quad, for example. It's trying to stay at a fixed point in space. If I try to move it out of the way, it fights me and moves back to where it wants to be. We can change this behavior, however. We can use mathematical models to estimate the force that I'm applying to the quad. Once we know this force, we can also change the laws of physics, as far as the quad is concerned, of course. Here the quad is behaving as if it were in a viscous fluid. We now have an intimate way of interacting with a machine. I will use this new capability to position this camera-carrying quad to the appropriate location for filming the remainder of this demonstration. So we can physically interact with these quads, and we can change the laws of physics. Let's have a little bit of fun with this. For what you will see next, these quads will initially behave as if they were on Pluto. As time goes on, gravity will be increased until we're all back on planet Earth. But I assure you we won't get there. Okay, here goes. You're all thinking now, these guys are having way too much fun. And you're probably also asking yourself, why